Hi everyone. In this pre-lecture video, I want to introduce the concept of something called convolution. So it's basically the idea of if I know the Fourier transforms of two things, what's the Fourier transform of the product of those two things? So basically we're thinking about, since we've worked out some simple Fourier transforms for a few functions, that if I have any product of those functions, so if I have a function which is built out of those functions which we've already investigated, we can calculate the Fourier transform of those very easily. So here's what it looks like. This is a reference from Hermann, section 8.6. So just to remind you, we've done these Fourier transforms before. So for example, the Fourier transform of a top hat function is this sine k over k. We have the Fourier transform of a Gaussian is another Gaussian. The Fourier transform of a delta function is a constant. So the question that we asked today is, like, suppose I had a function which was like the product of two of these. Like maybe I had a function which was a top hat function times a Gaussian. What's the Fourier transform of that? And is it equal to the product of these two Fourier transforms? So that's what we want to get into. Okay. The question is, suppose you have two pairs of functions which you know. Suppose you know that some function f of x, and it has a Fourier transform which we're calling f of k. And then you have a different function, g of x, and you know its Fourier transform, which is called g of k. Now the question I want to ask is, what's the Fourier transform of f of x times g of x? And the naive answer is, you might think, well, is it just f of k times g of k? And actually, the answer to that is no. It's a little more complicated. So we need to work out what exactly this Fourier transform is. Okay, so let me try to investigate it a little bit. So we'll take, let's define h of x is going to be defined to be f of x times g of x. Okay, so that function is the product. H is the product of f times g. And we want to know what is h of k. Okay, well, we can just use the definition for the Fourier transform. Of course, h of k, by definition, is equal to the integral minus infinity to infinity, h of x, e to the I kx dx. Okay, and so I could rewrite this f of x times g of x, e to the I kx dx, just like that. Okay, so now what I want to do is I want to get an expression that relates h of k to the Fourier transforms big F of k and big G of k. So what I need to do is insert into here the inverse Fourier transform of each of those. So I'm going to insert the formulas for the inverse Fourier transform. And those formulas, let me remind you, are these ones here. Okay, so I'm going to put those in up here. But before I do that, I'm going to make a change to the dummy variable because I don't want to have two k's floating around. You know, I've got integral dk, integral dk. It's going to be too confusing. So let me change the variables of these just to keep our integration variables straight. I'm going to call this first one, change it from k to something else. So I'm going to call it q, e to the I q x minus I q x dq. I can call the variable anything I want, right? It's a dummy variable. And let's call this one, instead of k, let's call it w. E to my psi w x dw. Okay, so all I did is I just changed the dummy variables of the integration there. And now we'll substitute those into this formula. Okay, so it's going to get a little bit ugly for a moment. So now h of k is integral minus infinity to infinity. F of x, now I got to put in what f of x is. So f of x is this whole thing, 1 over 2 pi minus infinity to infinity. F of q, e to the minus I q x. And then I got to put in what is g of x. G of x is this, 1 over 2 pi, integral minus infinity to infinity. G of w, e to the minus I w x dw. Sorry, and I forgot a dk here. Like that. And then I have out in front an e to the I kx dx. Okay, so all three of those integrals. So just to remind you, this is f of x. This is g of x. Okay. All right, now let's collect everything. I'm going to write it in a little more compact form. So let's collect everything together and put all the integrals out in front. So we'll put here, there's a 2 pi, 1 over 2 pi squared. So that's 1 over 2 pi squared. And I've got three integrals, minus infinity to infinity, minus infinity to infinity, minus infinity to infinity. All three of those integrals. And then I've got f of q, g of w, and let's put all the exponents together. So what do I have in the exponent? E to the I qx, e to the minus I qx, e to the minus I wx, e to the positive I kx. So let's combine all the exponents together. I get e to the I kx minus qx minus wx, right? D, and then all my different integration variables, dk, dw, sorry, it shouldn't be dk, it should be dq. So dq, dw, dx, like that, okay? And let me just write it a little more simply by factoring out an x from the exponent here. So I will have in the exponent e to the I k minus q minus w times x, just like that. Okay, now I got three integrals. It looks terrible, but I can do each of these. I can do the integrals in any order I want. Okay, and so what I'm going to do is I'm going to do the x integral first. So I'm going to bring in here, and I'm going to do the x integral first. So 1 over 2 pi squared. So I'm going to change it like this, minus infinity to infinity, minus infinity to infinity, and then I'm going to pull out the f of q and the g of w because those don't depend on x, right? Minus infinity to infinity, e to the I k minus q minus w times x. Do the x integral first. And then I have here, maybe it makes more sense to do it like this. dw, dq, okay? So I just switched the order of those integration variables, and I'm doing the x integral first. The things that don't depend on x I can bring outside of the x integral. So these guys here can come outside of the integral dx, because they don't depend on x. They're treated like a constant, come outside the integral. The only thing that has an x in it is this exponential, e to the I q minus w, k minus q minus w x. Just to remind you, this is h of k. Now this integral is something we've come across before. Remember, the integral minus infinity to infinity, e to the I something, let's call it, I'm not quite sure what to call it. Well, I guess I'll just call it k. X dx is delta of 2 pi times the delta of k. It's a delta function. Okay. So in this case, the thing in the exponent is k minus q minus w. So the integral of that, e to the I k minus q minus w times x dx is equal to 2 pi delta of k minus q minus w. All right, so let's write everything together. 1 over 2 pi squared. Now I have two integrals. I did one of them. F of q, g of w, delta, and then there's a 2 pi, which cancels one of these 2 pi's. So there's just 2 pi out front now. And then I have delta of k minus q minus w. dw, dq. Okay, but now remember, when I have something multiplying a delta function, it becomes very easy to deal with, right? So for example, maybe I want to do now it doesn't matter which, let's do the q integral. So let's do the q integral. So I'll pull the w out, so I'll have here 1 over 2 pi, integral minus infinity to infinity. And then I've got so the g of w will come outside because it doesn't depend on q. And then I'll have minus infinity to infinity, f of q, delta of k minus q minus w, dq, dw. Okay, so the inner integral is the one that depends on q now. All right, so let me write this a different way. Delta of k minus q minus w. That's delta of, let me write it like this, minus q plus w minus k. I think I got it right. Right, so if I distribute that minus sign through, I get minus q minus w plus k. And let me write that even a little differently. Delta of minus q minus k minus w. I think I got it all. Q. So inside the inner brackets, I have q plus w minus k, q plus w minus k. Seems good. Okay. But remember, delta is an even function. Delta of minus x is equal to delta of x. So I can ignore this leading minus sign, and I have q minus k minus w, like that. Okay, so what do I have in this inner integral? I have integral minus infinity to infinity, f of q, delta of q minus k minus w, dq. Okay, now this is a function times a delta function. The delta function has a spike when q is equal to k minus w. And that's the only point where the delta function becomes active. So this integral can be done using the delta function, and it just gives me f of k minus w. Okay? So I substituted in the point where the delta function is active into the argument of that function, right? F of k minus w. So I used this formula. Remember this one, minus infinity to infinity, f of something, f of x delta of x minus x0 is f of x0. So I just substitute in the point at which the delta function is active into the function in front of the delta function. Okay. All right. So what do we have all together now? Going back up here. The inner integral is very simple, so that's what I just did here. And let's collect everything back together now. H of k is 1 over 2 pi, still have that sitting there, minus infinity to infinity. I have one integral left, g of w, f of k minus w, dw. And that's as far as I can go. So this thing here is the Fourier transform of the product of f of x times g of x. This operation, where you've got an integral of two functions, one of them is shifted by a certain amount. So you can see, like, watch the variables. The variables I found very confusing the first time I did this. So k is the argument here, that k is this variable. And then w is the integration variable. And that, so w is the integration variable there. Okay. So the whole thing is a function of k, and w is being integrated over. So I've shifted the function f by an amount w, and then I multiply them together and integrate. And this apparently gives me the Fourier transform of f of x. This operation is called convolution. Which is the German word for folding. It's like the functions are kind of folded together in some way, and that gives me the Fourier transform. Sometimes written like this, so you'll see this notation, G star f. That's the convolution of f and g, which is a function of k. This is the definition, is defined to be minus infinity to infinity. This integral f of k minus w, g of w, dw. And by the way, it doesn't matter which one you shift. You can also write it like this, minus infinity to infinity, f of w, g of k minus w, dw. So it doesn't matter whether you shift one or the other. The order doesn't matter. You can shift either function. So let's write our result, which is called the convolution theorem. For Fourier transforms. Given two functions, f of x and g of x, and their Fourier transforms, let's call them big F of k and big G of k. The Fourier transform of f of x times g of x, the product of those two, is equal to, going back up here, 1 over 2 pi times the convolution of those two functions. 1 over 2 pi times f star g of k. And f star g is equal to g star f. The order doesn't matter. And that's defined up here. So f star g is equal to g star f. Order doesn't matter. So there you have it. That's how I calculate the Fourier transform of a product of functions. If I know their individual Fourier transforms, I do this weird convolution operation. I multiply them together with different arguments, do an integral, and I get divide by 1 over 2 pi, or divide by 2 pi, and that gives me the Fourier transform. Okay. By the way, it works in reverse, so you can do it in reverse as well. So let's say we have something like, what is the inverse Fourier transform of f of k times g of k? So again, suppose you know those two functions and their Fourier transforms, and then I have the product f times g of k. I want to know the inverse Fourier transform of that. Arguments are pretty much the same. We can kind of do it the same way. So let's call this thing a of k, f of k times g of k. And I want to know what is a of x, the inverse Fourier transform of that a. So again, let's just go through this one more time. A of x, by definition, is the inverse Fourier transform times a of k, which is f of k, g of k, e to the minus I k x dk. And then I will substitute in f of k and g of k. So remember, f of k is equal to the integral minus infinity to infinity f of x e to the I kx dx, and g of k is equal to integral minus infinity to infinity g of x e to the I kx dx. And then let's do the same thing. Let's put different variables in here. So let me call this the dummy variable something different. So let's call this one y. And let's call this one z. Okay. And substitute them in, again, up here. What do I have? A of x. Three integrals, minus infinity to infinity, minus infinity to infinity, minus infinity to infinity. Three integrals. I have f of y, g of z, and let's do it all in our head. Let's combine all the exponentials together. So I've got here e to the I z plus y minus x times k, just like that. And then I've got dk, dy, dz. Doesn't matter which order I write those in, because I can do the integrals in any order I want. Okay, now do the k integral first. The y and the z come outside, so I get 1 over 2 pi minus infinity to infinity, minus infinity to infinity, f of y, g of z, and then I'm doing my k integral, which looks like this, minus infinity to infinity, e to the I, z plus y minus x times k, dk, and then later do the dy and the dz integrals, right? Okay. This integral is a delta function, as usual. So this is 2 pi delta of z plus y minus x. And so we have two integrals, but one of them I can do with that delta function. F of y, g of z. The 2 pi cancels this 2 pi out in front, so I don't need that one anymore. Delta z plus y minus x dy dz. I'm going to do the y integral, so I'm going to write this thing as delta of y minus z plus x, right? If I distribute the minus sign through, I get y, whoops, I screwed it up. What do I have to have here? I have to have y minus minus x minus z, like that, right? Because the z comes with a plus sign and the y and the x comes with a minus sign. Okay. Do the integral over y. So that's integral minus infinity to infinity. Now g of z comes outside. F of y, delta of y minus x minus z, dy dz. This integral gives me f of x minus z. Right? And so finally, what I'm getting here is a of x is integral minus infinity to infinity, g of z, f of x minus z, dz, which again you will recognize as a convolution operation. This is f star g of x. So we can write a kind of alternative statement of the convolution theorem. This is like another statement, alternative. given two functions, f of x and g of x, and their Fourier transforms, f of k and g of k, the Fourier transform of the convolution f star g of x is f of k times g of k. And what we wrote above is kind of the inverse of that, right? Which is like the inverse Fourier transform of the product f of k times g of k is the convolution f star g of x, right? I guess I could write that as well. The inverse Fourier transform of f of k times g of k is f star g of x. Okay. So these things are quite confusing the first time you see them, but I think doing some examples will help, and we'll do some examples in class. So we have let me summarize these two statements. The Fourier transform of a convolution is the product, and the Fourier transform of a product is the convolution. So if I have this function which is the convolution of two functions, their Fourier transform is the product of the two. And the one I had above is that the Fourier transform of the product of these two is the convolution of the Fourier transforms. Okay. So doing some examples I think will help. We'll do some, now we can go back up to the beginning and say what if I had a function which is a Gaussian times a delta function, and I want to know the Fourier transform of that. I know how to do it because I know their Fourier transforms, and I can do that convolution operation. Or what if I had a top hat times a Gaussian? I could figure out the convolution of those two functions, and that would tell me the Fourier transform of the top hat times the Gaussian. So some examples will help, and we will do some examples in class. Thanks for your attention. I hope you found this little pre-lecture useful.